Okay, chemistry. So this week we're going to worry about light and how light can interact with an atom, specifically with the electrons in an atom. And this is a really useful tool for chemists. So this is the core mechanism behind how we can look out into outer space and understand the chemical composition of distant stars and distant planets. It's also how we can understand and investigate elements that we have here on Earth and compounds. And lastly, it's also how we get light out of things like light bulbs. So really important connection to make here. So let me help you think through this. The one key question to think about, so you know what a wave, you've seen ocean waves, but where does a wave actually exist? So we see it when it crashes on the shore, and you can see it percolating out in all directions from a rock dropped in a pond, but that wave actually exists in multiple places, right? So you have sort of a ring that is where that wave exists. And ocean waves are just energy passing through water. Right? And in the same sense, we're going to have things that contain energy and will exist in more than one place, just like our ocean wave exists in more than one place. It's all over the place. It's a discrete thing we can point at, we know it when we see it, but it doesn't exist in a single place. A really important concept here. So this is also going to be true for electrons. So electrons have several properties, so mass, charge, spin, that contain energy, but also they behave like waves. This becomes important when we get to really small things. So everything behaves like a wave a little bit. Your desk in front of you behaves like a wave, but it's really not significant the level that you live at. But when you get down to really tiny things, that wave function of matter becomes really important. And so this is one way to think about it. Let me show you what this looks like on a simulation. So here's the basic idea is that we're going to have places where electrons can exist, and those electrons are going to exist essentially as waves, and those waves are going to be spreading around. So this is one example of how to think about it. So I essentially have like a stationary wave. You can see this purple thing oscillating in and out, and so my wave can exist at this location. I can move it closer to the nucleus, and it can exist at another location. Right? Notice that the number of humps changes, so we call it the antinodes. The number of antinodes changes as I get closer, and so on. So the key thing, and really important about electrons, so we can't really tell where a specific electron is at any given time because it's kind of spread all over. It's like asking, well, where's the wave at this point? And you can't really point to it. So electrons do have an area where they exist, but they don't have a specific location they exist. So it adds a little bit of complexity to things. But electrons have energy, and they're represented by a wave. So where they exist, though, is something that we're going to call an energy level. Now, let me describe what we mean by that. So energy levels are going to be sort of these geographic locations outside the nucleus. I think think about like layers of an onion. So as you go out, you have another layer of the onion. You get to the outside edge of the next layer. So you can have these places where electrons exist, and we'll call these energy levels. And we'll number them from the nucleus outwards. So energy level 1 is close to the nucleus, energy level 2 is further away, and so on. So each of these areas or energy levels is a place where electrons can exist. But think about what this means, though. So there are places where electrons cannot exist. And so I can't have an electron hanging out between energy levels. So it's really a curious thing, and it has to do with it being a wave and having wave properties. So it has to exist at some number of antinodes. But you've come across something like this before, right? So you've walked up and down staircases, right? You can't get to the top of a staircase by taking half steps. If you want to go up, you have to take a full step, right? Just like an electron, it can't get to the next energy level by doing half a step twice, right? It doesn't get you anywhere. You have to have at least enough energy to get you to the next energy level, just like you have to have a big enough step to get you up the staircase. So this is the idea of quantum, right? So you come across this idea of quantum where something can exist in one state or another state, but not really in between. And this is one of the better examples of quantum effects that we can learn about at this level of science. I mean, it has a huge effect as you get into smaller particles, and the world is full of sort of quantum things like this, right? So you have a left shoe and a right shoe, right? That's quantum. It's either a left or it's a right. You don't have something that's in between. And an electron is going to be the same sort of thing, that it exists at an energy level number 2, or it can exist at energy level number 1, but it's not going to exist between the two of them. Really important. Okay, a few important things about the nucleus. So nucleus, it contains protons, it has a positive electrical charge. Electrons are negatively charged, so hopefully you know that opposites are going to attract. So my electron is attracted to the nucleus, but it can't get there. So this is important, right? So my positive and negative charges attract to each other, but it can't get there because of this wave property that it has. So it has energy, and it's essentially in motion, and because it's a wave, it just can't get to the nucleus. Right? In particle accelerators, you can smash them together and force them together, and then weird stuff happens. But in everyday chemistry, they don't get there. It's attracted, they try to get as close as they can. So when we have more than one electron around an atom, there's this competition that's happening. So we have electrons are being attracted to the protons in the nucleus, so they want to get closer. But then electrons have the same charge as each other, so they're trying to get away. And so it's this balance between being attracted to the nucleus and trying to get away that we'll get into in a little bit, that describes or helps us understand how electrons get arranged. So for right now, we're worried about what happens if we just have a single electron that's around a nucleus, and hydrogen is a convenient example for that because there's only one electron around hydrogen. It's got one proton. So we'll use that for the example right now. So we're going to try to use this and understand, well, what happens when we add or remove energy from an electron, right? And wait a minute, how do we even do that in the first case? Well, remember where we started, light. So recall that light is energy. So a good way to think about light is it transfers energy from one place to another place. So we'll use light to add energy into an electron. And you've already seen this. So last week you looked at the photoelectric effect. This is exactly what we're doing. So we're sending light into metal in that case, and it's absorbing that energy. So those electrons are absorbing that energy from the light. And what it does is it then moves the electron further away and to a higher energy level, and then the reverse can happen as well. So let me remind you what this is going to look like. So this is the simulation we're going to ask you to do this week. So to take a look at how this happens. And I've set this up, right? So here I have an electron. It's a ball. It's shown as a ball here. It's not really a ball, right? It's all over in here someplace, right? So I don't know where. So I'm going to shoot some light into it. So you see this photon of light coming into it. It's going to hit it. And what happens, it sends it out of the frame. That wasn't it. I forgot to reset this. So let me go to 2.6, 6, and I'll go to the second energy level. Okay, let's try this again. So I'm going to shoot some light into it. It's going to hit my electron. No, it misses my electron. Let's try a little bit higher energy light. So now it has enough energy. So what happened, right, you saw that, so it vibrates and gained the energy, and the way it gains energy is by moving further away from the positive charge, right? And I think about this in magnets, as if magnets, right? So if I have two magnets that are stuck together and I want to move one further away, I have to add energy into that, right? That costs me energy to pull those apart. And so what we're doing here, right? We're pulling apart things that are attracted. I'm pulling apart an electron and a proton. That costs me energy to get it further away. So importantly, an electron further away has more energy. And that's why I call it energy levels, right? So the first energy level is the lowest energy, second energy takes more energy, third, fourth, so on. So as I move further away, it takes more energy. But I could do the reverse, right? So notice what happens. So I sent here, let's do it again. So I sent a piece of light into it. That light energy was absorbed. That light no longer exists. That energy has now been converted into moving this electron further away from the nucleus. But I can do exactly the reverse. So whatever photon of light was absorbed here, when I move it, now I'm going to move it down to the second energy level, that same photon of light gets released. Right? So notice this is an entirely reversible process, and this is how absorption spectra works. This is how we can look at distant stars. We see, well, what light gets absorbed, and also as emission spectra, we see what light gets emitted. So I'm going to shine light at it. My electron is going to absorb that energy, move to a higher energy level, and then when it moves back to a lower energy level, it's going to release that energy in the form of a photon of light. So this is what we're going to try to help you get your head around. So this is, now we're getting outside of the nucleus of chemistry, and we're working with electrons and how they can move around and some of the consequences of that. And this is one of the fun parts about chemistry. We get to shuffle things around. So key thing, light transfers its energy to an electron and moves to a higher energy level. We'll call that an excited state. And then when it goes back down or returns to the ground state, then it released that exact same photon of light. But it's got to be the right photon. Anyway, that's the plan for this week. We'll give you a chance to get your head around it. And then we'll start using that a little bit to try to understand a number of things, including how you can get colors out of things, and how fireworks can give off colors, and how light bulbs can give off light, and how the atom itself can be understood. I hope that's helpful. Talk to you soon. Bye.